Hello everyone and welcome back. What we're going to talk about today is using radicals, and radicals are a very difficult concept because you're trying to talk about things that could be eventually multiplied by themselves enough times to get us back to a number. It becomes very difficult to kind of look at all of these ideas as being the story behind their creation. There's just so much there. But if we can take a moment and we can just acknowledge that radicals will happen because I'm allowed to exponentiate, I'm allowed to take things and raise them to an exponent to grow their size or to at least repeat that multiplication, then I can do square roots, cubed roots, really any kind of root to bring that process back to its beginning. That if I am just allowing myself to accept that there is in fact a number that is at the end of all of these operations, then there's no reason I can't treat it using all the same properties and ideas that I normally would for numbers. So let's go ahead and jump in to how we're going to be working through the notes for today. So today is all going to be about, can we balance this confusion in our head with what exactly things are, and then kind of temper that a little bit with saying, but I understand how they behave, and sometimes that's enough for me. So if you haven't already, I highly encourage you to go watch this video. Math Isn't Hard, It's a Language by Robert, I hope this is right, Palisak. It's a really good video where it talks about how even young kids can think about really difficult ideas like adding billions and adding variables and fractions if they just take a moment to be comfortable with the language in the same way that I was talking about before. So we're going to instead look at, we're going to assume that you've watched that, and we're going to click into how we can use these radicals to model this behavior that I'm talking about. So let's take, for example, this square root of 15, and I'm adding 7 more square roots of 15. Imagine we didn't even know what the square root of 15 is. We didn't even know what it meant. We're going to trust that it is in fact a number. And imagine that I'm so frustrated by the fact that I don't know what square root of 15 is that I don't even want to look at it anymore. I'm going to cover it up, and I'm going to say, you know what? That's just, I'm going to put an X there instead. And I'm going to do that every single time I see one of these numbers I just don't understand. It's perfectly fair for me to say that by adding a square root of 15 to 7 square roots of 15, it's the same as adding some x, some unknown thing, to 7 more of those unknown things. Well, that might help to simplify this out. We have 8 of them then. We have 8 of these x's. And similarly, we would have 8 of these square roots of 15. So we get an idea of this behavior of logic. We know that 15 is some number that if I multiplied it by itself, so we get the square root of 15, and if I multiply it by itself, it means that I have the square root of 15 squared. And since the square root of 15 means take 15, use it as the size of a square, tell me what number started that's the number that would be my side, and then by squaring that number, I should go back to creating a square again. I've just kind of done and undone this whole process. So really, I'm just right back to 15. So this idea of saying square root of 15, it is a number, and we can pull up a calculator and we can try it out. So let's just pull up our simple calculator from our computer, and we'll try to do the square root of 15 with this. So we're going to change it over here to our scientific so we have some more buttons to play with. And here we go. We're going to type in square root of 15, so 15, and then we're going to attempt to square root it. And our calculator is going to give us this long, hairy number. It's a number. It absolutely exists. It's pretty close to all the digits you see on the screen. It's pretty close to 3.829, etc. My calculator doesn't have all of the digits it would actually result with because it eventually runs out of space and assumes that I just don't care enough to look at the 200th decimal point. But there is a number out there that exists such that if I multiply it by itself, I will get to 15. And just to show you that, let's go ahead and do that. We'll raise it to the power of 2. So we'll click our little exponent button here, and we'll raise this button to 2, and hopefully, yep, it gets us right back to 15. So it's just the undoing of this repeated multiplication that we're trying to capture. But instead of writing all those decimals, because if we tried, we would have to eventually stop, and if we stopped, we would be imprecise, we're just going to have to recognize that some of these numbers are just going to be best written by the method we use to get there. Now, again, if this feels weird, let's try to find a parallel. For example, what if I gave you the number 1/3? And you might think that this is a number. And it is a number. But think about how you're describing this number. The number 1/3 is the number that results from 1 trying to be divided into 3 parts. That's why it looks very much like a division symbol whenever you have a fraction. It's talking about doing division. This equals 1 divided by 3. So it's not uncommon for us in math to be talking about numbers as being the thing that results from trying to do an operation, because otherwise we would have to write something very imprecise like 0.33, and then maybe we could choose to use decimal points to show that it goes on forever. Maybe sometimes we show that there's a repeating bar and that it goes on forever. But again, hidden in all of this is just us trying to capture a number that we can't write in the traditional way. All right, enough about that. Let's see if we can now go on to some of these other problems. So I now have 10 square roots of 5, and I'm taking away 9 fourth roots of 5. So that means that the fourth root of 5 is a number that if I raised it to the 4th power, I would get back to 5. The square root of 5 is a number that if I raised it to the 2nd power, I'd get back to 5. Those are not the same thing. So I could think of this as being 10 x's minus 9, I can't write x's again, it's something else, it's something different, 9 y's. Well, can I combine x's and y's? If I say that I have 10 apples and I take away 9 oranges, is that something that allows us to get to a simple conclusion? It's not a statement that can be subtracted. They're not the exact same thing. So some of these things are not going to be able to be simplified. It's going to have to be left as it is. This is already in its most simplified form. Okay, let's look at another example, something that might be something that looks even more difficult. Okay, so we've got all this here. So I've got the square root of 54 plus 6 of the square root of 72 minus 3 of the square root of 24. Again, I have a whole bunch of different things that are being added and subtracted together. I might not be able to, or I might think that I'm not allowed to simplify this anymore. But here's the difference between having numbers to start with versus variables. We, as mathematicians, can look at these numbers and realize that they can be rewritten in ways that might allow them to be related a little bit easier. Let me show you what I mean. We're used to taking 54, and we could look at it in 54 instead as its factors. We could look at it as all of the little building blocks that compose this number 54. And so we could look at that as 2 times 27. And instead of 27, we could look at that as 3 times 9. And instead of 9, we could look at that as 3 times 3. Similarly with 72, we could look at 72 as 3 times, what would that be then? 24? 24. That would be then 3 times 8. That would be 2 times 4, and then 2 times 2. And then 24 could be simplified, or it could be, I should say, factored into 3 and 8, 3 and 8. And then 8 can go down to 2 and 2, or 2 and 4, and 2 and 2. So notice that the pursuit here is almost like we're just playing with the numbers. We might have originally thought that they couldn't be simplified anymore, but perhaps if we can change our perspective, we'll be able to find a different way of expressing the same idea. So let's take a look. If I looked at the square root of 54, that would be the same idea as saying that I have the square root of 2 times 2, or excuse me, 2 times 3 times 3 times 3. And that for the next one, instead of looking at 6 groups of square root of 72, I have 6 groups of 3 times 3 times 2 times 2 times 2. And then for the very last one, that would be, instead of plus, we have minus 3 groups of, and instead of root 24, we have 3 times 2 times 2 times 2. Okay, why would we want to do this? Well, if the idea is that we have the square root being this process of me trying to find what number originally I started with in order to get a square, then let's run that idea backwards and say that 3 times 3 would get me a 3 square. 3 times 3 would get me 9, and if I tried to square root 9 and figure out where that 3 square came from, I could replace everything on the inside of the square root with just a 3 on the outside. So we could rewrite this as saying that this entire expression could now be written as a 3 on the outside and a 2 times 3 that don't have any other matches for me to be able to square root them easily. Okay, so we're doing so good so far. Now I've got 6. Is there anything that I can bring out front of this square root? Well, I have a 3 times 3, and I have a 2 times 2. So I could bring a 3 and a 2 out front. So that would be 6, and then 3, and then a 2, with a square root of 2 being left over. For the very last one, let's see what kind of pairs we can find. I have a pair of 2s that can be brought out front, and that's just about it. So then I would have 3 times 2 that I bring out front, square root of 3 times 2. So all in all, I can rewrite this entire expression as being 3 square roots of 6 plus 6 times 3 is 18, times 2 would be 36, so plus 36 square roots of 2, minus 3 times 2 would be 6, so minus 6 square roots of 6. And here we actually find that there's an overlap. I could have written this entire thing much more simply. I could have written it as 3 minus 6, so I have 3 square roots of 6, and I'm taking away 6 square roots of 6. That gives me a total of negative 3 square roots of 6. And then my 36 square roots of 2 have nothing else that they can partner with, so those will stay as they are. Now, it might feel a little bit weird about why is it that we're going through all of this effort in order to simplify something that still looks generally kind of complicated. And we're starting with something that looks definitely more complicated, but we're like, is the effort worth it? I'm going to let you know what my logic is for this. I think it is logical to be saying that we're going to try to simplify expressions, because whenever we're trying to communicate our ideas to people who are working independently of us, so imagine that you're in your future job, you are trying to accomplish a project, somebody else is trying to accomplish a project, and you'd like to share ideas. If you begin the conversation from a place that you both understand and that you've both kind of related to, it makes the conversation go easier. You can share ideas much better. But if instead you both try to speak in your own language, or you try to speak about your own ideas without an attempt to relate them to each other, you're not going to get very far when you're trying to talk with people in different fields or in different companies. This is the same idea. If you look at numbers like square root of 54 and square root of 24, they may appear as if they aren't the exact same. But hidden in all these details is that you actually have those two numbers being much more common than you would have thought. So taking time to simplify, taking time to break things down until you get really the simplest version of them is a useful exercise, so that you can find out when patterns are emerging, you can relate them to other ideas that popped up in your head, and possibly other times that you've seen these numbers before. Okay. So we have this idea of saying that I can factor things down, I can look for these overlaps, these groups of 2 and pull them out front of square roots. Similarly, I could look for groups of 3 and pull them out front of cubed roots. How can we tackle really difficult problems like this letter D? A lot more simply than you might think. The first process that I would recommend we do is see how much we can simplify these in order to find any potential overlap. So if I'm looking now at the cubed root of all of this craziness, then that means that I am trying to take items that are being multiplied by themselves 3 times, and I'm trying to bring them back down to their root, which is just one of those instances. So here I've got 27. How can I think about 27? 27 can be thought of as 3 times 9, and 9 can be thought of as 3 times 3. So now I could rewrite this as the cubed root of 3 times 3 times 3 times m to the 5th power, but you could actually expand that out if you wanted. So it'd be m times m times m times m times m, and then you've got 4 of those n's. Okay, so we've got n, I'm running out of space. I'll just put it as n to the 4th, but that'd still be n times n times n times n. All right, so just on that very first term, how could we rewrite this? Well, we could rewrite this as looking for those groups of 3. Here's a group of 3 3s, so that means that the place they originate from, that origin, that root, is just going to be one of those 3s. Here I'm looking for groups of 3 in the m, so there's a group of 3 in the m, and that's about all the groups I have. So I can pull one of those m's out front as saying that is my origin for 3 of them being multiplied by each other. And then I have 2 m's left on the inside. What about that n? Well, similarly, you could imagine it's expanding that out and then finding 3 of them and taking them away. So you can really kind of in your head come up with this shortcut of saying that if you want to bring something out front, you're really bringing one n out every time you bring the number of n's down by 3. So overall, you can simplify this entire first term as saying that you now have the cube root of m squared times n, because the 5 that was originally with the m, one of them is now out front, which left you with 2. The 4 that was originally with the n, one of them is left over, and 3 of them were taken out. And for the 27, none of them are left over because all of the 3's were taken out. Let's see if we can do the other two just as quickly. So now we've got plus 2 times m times n that are on the outside, nothing happened there. Then we have the cube root of, and we're looking to pull things out from m squared and n. Well, I can't pull out 3 instances of m if I only have 2 of them on the inside. If I only have an m squared, that's just m times n. And if I'm looking for 3 of them to kind of partner together, I don't have enough, so we're gonna have to leave that as it is. That's gonna be an m squared left over. Similarly with the n, that's gonna have to be left over. Okay, no problem. Let's look at the very last term. So now we're trying to pull out groups of 3. We have the m that's still in front. I'm trying to pull out 3 from the m squared. Again, I don't have enough, so we'll have to leave that as it is. And then I'm trying to pull 3 out from the n to the 4th. Oh, I can do that. So there'll be 1 left over, and there'll be 1 out front, because that's one group of 3 that I was able to pull out front. So I've got minus m times n, and then cube root of m squared n. Well, take a look. All of these actually overlap, and we might not have seen that originally. This can actually be rewritten so much more simply. So I have 3 mn of these cube roots. I am adding 2 more mn of these cube roots, and then I'm taking away an mn of these cube roots. So if this becomes very odd, you could think of this as saying 3, and maybe mn is too much. Let's cover that up. Let's ignore it. Let's give it a label. We'll call it x. So every time I see mn, I'm just going to cover that up with x. And every time I see cube root of mn squared or m squared n, I'll say that that's just y. It's the same thing as the language of you saying that you have 3 xy's, you're adding 2 more xy's, and then you're taking away an xy. If this feels weird, don't worry about this line. I'm just showing that if you want, you can cover up these ideas with language, with different labels, and it's still the same idea. These are all like terms. 3, and then adding 2 more gets me 5, taking away 1 gets me back down to 4. So whether you want to include this little kind of partial moment step in our math or not, you can think of this as saying that I'm going to be left with 4 of these mn cube roots of m squared n. Kind of crazy that we can do all of this math with numbers that are hidden in its cubed roots, that are being multiplied. We don't even know what they are. It doesn't matter. If we understand how addition works, subtraction works, we understand how exponents works and roots work, we can simplify really, really large expressions like this into something that is much, much simpler. Saying that we have just 4 of these things, some of which I was able to cube root effectively, some of which I was not able to cube root and had to leave them where they were. Let's take a moment and look at how, even if we have some complicated expressions like fractions, again, this is no different in that you actually have all the tools you need to handle these problems effectively. It's just a matter of making sure that we're using our language, our visual aids, our knowledge of properties to really kind of fall back on and to tackle this elephant by eating it just one bite at a time. So let's imagine that I wanted to try to subtract these two different numbers, right? Everything here together is just a number, so we can treat it with the same properties that we've been practicing with all this time. Well, there's nothing to say that I can't try to make this more simple on myself. So let's do the exact same thing, where now I'm going to try to take 45 and I'm going to break it into its components. Oh, 45, break it into its components. That's going to be 5 and 9. That's going to be 3 and 3. Okay, so that means that I can think of this square root of 45 as being a group of 2 3's. So I'll pull a 3 out front from the square root and I'll leave the 5 behind. So remember, square root means that I'm looking for repeats that would have gotten me a square. So I'm pulling one of those out front to say that the square would have originated from just one of those 3's. All right, so I've got 3 square roots of 5 divided by 6x. I'll have to leave that as it is for right now. And then minus 4, can I do the same thing with 20? Let's try it out with our little factor tree. So 20 can be thought of as 5 and 4, which can be thought of as 2 and 2. So I have another grouping that I can pull out front. Here's a 2 square. 2 times 2 would be a 2 square, and that 2 square would have started from the number 2. So I can pull out the number 2, and I can leave behind a root 5. And then that gets me 5x. So all in all, I can rewrite all of this as saying that I have the 3 square roots of 5 that are still over 6x, and I'm trying to take away 8, square roots of 5 that are over 5x. Well, that would have been easy if I didn't have these fractions in the way. I really wish I could get rid of these fractions. How could I get rid of these fractions? Well, if I normally wanted to subtract fractions, what would you do? You'd probably do common denominators. So let's see if we can use common denominators, this thing that we would have normally done if they were numbers, to help aid us in simplifying this expression. So I'd like to find a common denominator between 6x and 5x. I'm looking for something that I can multiply up to that would get me all of that. Well, the first thing that you might want to recognize is that you can always create a common denominator just by multiplying the left fraction by everything that it's missing and multiplying the right fraction by everything that it's missing. So I'm going to do this problem quickly in 2 different ways. The first way is I'm just going to do kind of the lazy approach and realize that if I'm lazy about it, I'll probably have to simplify more later. And then I'll show you the elegant approach we can see if we are a little bit more careful after we finish. So this is the lazy approach. The lazy approach in my mind is that if I have 3 square root of 5 and there's a 6x on the bottom and I want to eventually have it be shared with this 5x, let's just put the 5x there. I want to put the 5x on the denominator. I can do anything I want in math so long as I balance it out. So I'll balance it out by multiplying by the top as well. Notice that the reason why I'm multiplying by 5x on the top and multiplying by 5x on the bottom is that multiplying on the numerator means multiplication and multiplying on the denominator means division. So I can do this to the top and bottom so long as, or because it comes back out to the same meaning. All right, and so then I'm subtracting. I have my 8, I have my square root of 5, I have my over 5x, and I really want the 5x to be sharing a denominator as well. So I'll put 6x over here, and I'll put 6x on the top. Same logic applies. So all in all, I could think of this as saying that I have 15x square roots of 5, and I'm taking away, 6 times 8 would be 48, I'm taking away 48x square roots of 5. All over 6 times 5 would be 30, and x times x would be x squared. So now I've got one fraction instead of 2. It might look complicated, but we're making progress. We went from having 2 unrelated fractions to having, let's see, or with unrelated numerators, to 2 unrelated fractions with related numerators, to 1 fraction with related numerators. So we can keep on going. 15x of these square roots of 5, and we take away 48x of these square roots of 5. That means I have 15, and I'm taking away 48 of the same thing. That would leave me with negative 33. Okay, so we have negative 33 of these same things. And on the denominator, we have 30x squares. How can we simplify? Well, there's an x on the top and there's an x on the bottom, so I can take care of that. I'll take away 1 from here, and I'll take away 1 from here by removing the exponent. And then I could reduce this to negative 33 square roots of 5 over 30x. And then we could also see that the top has some 3's in it, the bottom has some 3's that are able to be factored out. So if I divide the top by 3 and the bottom by 3, that gets me a negative 11 square roots of 5 over 10x. And I think that's about as far as we can go. So take a look at just this simplified answer over here and imagine, would you have thought that things that started with 6's, x's, 45's, and 20's would have eventually been able to be combined so easily? This is where we get to see that there's actually a kind of hidden overlap between these 2 different types of numbers, and that we can write them much more simply just like this. Oh, we were going to talk about that shortcut. What could we have done instead of multiplying by 5x and by 6x on both sides? Well, we might have been able to recognize that there was already an x that they shared. So the thing that we were missing wasn't just the 5x and wasn't the 6x respectively. It could have just been that we multiplied one by 5 on the top and bottom and the other by 6 on the top and bottom. Then they would have had everything they need on the denominator. I'll leave that for you as an exercise. We would call what I've created here a common multiple. But if I had recognized that they already had their shared x, and I only needed to make sure that the numbers grew to match each other, that would have been what we call our least common multiple. And it would have made our simplifying right here become unnecessary. I'll leave that for you to kind of play around with. All right, let's start to build up some of the speed for these problems so that we can do question C when we get to it. So now I'm looking for groups of 4 to pull out front of my 4th root. In my a to the 5th, that would be one group of 4 I could imagine being there. So I'll pull 1 out front. I've got a 4th root of a that's going to have to remain because I can't pull it out front. That'll be over 3. And then I have plus a fourth roots of a over 12. All right, I'd like to get these to be a common denominator because that's how I would normally try to add and subtract fractions. I could multiply both sides by, I could multiply the left fraction by 12 and the right fraction by 3, or I could be a little bit more clever and recognize that I could just grow 3 up to 12, and that 12 is my lowest common multiple. So that would be, I could get 3 up to 12 by taking 3 and multiplying it by 4, and then balancing that by multiplying the top by the same thing. So that'd be fourth root of a times 4. Then I have plus a fourth roots of a over 12. All right, so that gets me 4 of these a fourth roots of a over 12 and a fourth roots of a over 12. And I'm adding these together. Well, if I have 4 of something and I'm adding 1 more of these somethings, all in all, that's going to get me 5 of these somethings. 5 of these a fourth roots of a over 12. Not too shabby. Nothing I can simplify because there are no a's in the denominator to cancel away, and my 5 and my 12 have no common factors, so I can't pull anything out there. Let's look down at the last problem. This might look crazy hard, but we're going to try to go through it quickly using the same properties and shortcuts that we've been developing along the way. So we have a square root here. Notice that square root means that I'm looking for groups of 2 so that I can pull one of them out front as a representative, if you will. So now we'll have 3x cubed. I can pull, let's see, 24. Let's do our little factor tree for 24. 24 would be 4 and 6. 4 can be broken down into its prime factors of 2 and 2, and 6 can be broken down into 2 and 3. So all in all, I can say 3x cubed gets carried down. I have a group of 2's here, so I'll pull 1 out front. Have to leave on the inside the 2 times 3, so I'll have to leave a 6 behind. What else can I pull out front? I can pull out front 2 of these x squares, or 2 of these x's, so I'll bring out 1x to show that. So I pulled out a 2, I'll pull out an x, and I'll pull out a y, and left behind I have 6x and a leftover y as well. On the denominator, what are we going to have? We're going to have 2x. I can look inside my square root and see that I can pull out another x, and that I'm going to have to leave behind my 3 and my y. Okay, subtract that away. Now I've got x squared. I'm looking to pull something out of 10, so let's make a little factor tree. We've got 2 and 5. No groups there. I'm going to have to leave everything as it is. Can't pull anything out from the x, and I can pull out 2 representatives from the y to the 4th. So I'll pull out 2 representatives of y to the 4th, and then on the inside I'm going to leave my 10 and my x because there's nothing I can do. On the denominator, I now have, let's see, 5. 5, I can't break 5 down. There's no prime factors for 5 besides 1 and 5, so that's not going to be any help. And the y squared, I can bring out a y. We'll bring out a y. And leave the 5 behind. Okay, let's try to simplify all of this. This would be 3 times 2 gets us 6, so we can write 6 in the numerator. We have x cubed times x, that gets me 4 x's that are in all being multiplied. I have a y that's on the outside. On the inside, I have 6xy. On the denominator, I have 2x squares and a a square root of 3y. And then I'm taking away x squared y squared times square root of 10x over y square root of 5. Oh, golly. Okay, what can we do that can simplify this all into one fraction? I think we're going to have to do the same thing we did when we had these uncommon denominators. Again, we're just subtracting fractions. If I ever want to subtract fractions, I can do that by getting a common denominator. So let's use a different color here to keep track of our work. What is the denominator on the right hand missing? It's missing a 2. It's missing an x square. It's missing a cube root of y. It's missing everything. Oh, golly. Okay. Excuse me. A square root of 3y. And then I would need to multiply by the top to balance that out. So x squared and then square root of 3y. Okay. I'd have to get the left fraction to match the right fraction as well. So what can I miss over here? I need a y and I need a square root of 5. And we'll do that to the top to balance it out. All right, not changing the meaning, just changing the appearance. Let's see what we can do to simplify all this out. The next line of work would be, now on the outside of the first fraction, I have 6. That's going to be left alone. X to the 4th, nothing affecting that. I have 2 y's that are being multiplied on the outside of a root, so that could be a y squared. On the inside of the root, I could look at that as the square root of 5 and 6 would be 30, and then I have x and I have y. On the denominator, I have 2 x squares. I have a y. On the inside of the square root, I have a 3 and a 5 gets me 15, and I have a y. I'm then going to subtract away. On the top, I have 2. I have x squared and x squared on the outside. That'd be 4x's in total being multiplied. I have a y squared. And then on the inside of the square root, I have 10 and 3 makes 30. And then I have an x and a y. On the very bottom, on the denominator, on the outside, I have 2 x squares. I have a y. On the inside of the square root, I have 5 and 3 gets me 15, and then I have a y. Oh golly. Well, I think I might have something that I can combine here. Oh, and even more so, do you see all the parallels? Do you see all these places we can combine? Look at all these. We've got a square root of 30xy. We're going to be sharing on both sides. We have, in fact, the whole x to the 4th y squared. That's the common on both sides. So we have 6 things, and I'm taking away 2 things. And the denominators are the same, so now I can combine those fractions. So all in all, I have 4 of these things, these x squares, or x 4th y squares. Y squares, square root of 30xy's, and it's all over 2 x squares y with a square root of 15y on the inside. Are we done? We can go even simpler, keep pushing it. I have a 4 on the top and I have a 2 on the bottom. 4 divided by 2 is going to leave me with just 2 on the numerator. X to the 4th, I have x to the 4th in the numerator, and I can divide 2 of those away from the x squared on the bottom. That's going to leave me with 2 on the top. I've got y squared and I'm taking away a y from the bottom. That's going to leave me with a y. Okay, so that's now 2, and on the top I have x squared y. And then what about in the square root? Well, I could look at that as the top being squared and the bottom being squared. There's nothing but multiplication and subtraction happening. So I could look at all of that as just being the top and bottom still needing to be square rooted, where the top is 30xy, and the denominator is my 15y. 2x squared y. On the inside of the square root, 30 divided by 15 gets me 2. X and there's nothing to cancel with the x, but the y is on the numerator and the denominator. That goes away. I think we've got this fully simplified. Look at this one. 2x squared y times the square root of 2x. That's what all of this craziness comes out to be. It comes out to be just one coefficient times some numbers that I am not yet aware of yet. If any of this feels weird, if any of the steps that I did here were odd for you when I was moving around the variables, when I was readjusting the square roots, I encourage you to try this out with numbers and to convince yourself that what I was doing with these symbols is the exact same thing we'd be allowed to do with numbers. So for example, I kind of glanced over the fact that here I took the square root on the top and the square root on the denominator and I made it into one big square root. Is that a thing that I can do? Well, let's check. If I had the square root of something on the top, let's say maybe 4, and I was trying to divide that by 9, that would be equal to, actually let's do, yeah, that'd be fine. Would that be equal to, with a little question mark, would that be equal to 2 over 3? In other words, where I square root the top and I square root the bottom. Maybe we'll write it that way. Is that equal to, so we'll do a question mark equal to, is that equal to square root of 4 over square root of 9? In other words, is that equal to 2 over 3? Okay. Well, the way that we can ask ourselves this is if I started with 2 over 3 and I wanted to try to use it to make a square, would I get back to my 4 over 9? In other words, if I took 2 over 3 and I multiplied it by 2 over 3, would I get to 4 over 9? So that'd be 2 over 3 times 2 over 3. And sure enough, if you multiply the top, you get 4. And if you multiply the denominator, you get 9. So if I ask you, where did this 4 over 9 come from? Where did this square that is 4 over 9 big come from? Where's its root? Then you're looking for a fraction, such that if I took this and I used it to make a square, that I would get back to where I started. And so yeah, it's absolutely okay for me to say that if I have a square root of the top and a square root of the bottom, that means I have a square root of the whole thing. And if I have a square root of the whole thing, I can look at that as the square root of the top, and I can look at that as the square root of the bottom. Now I want to take just a moment and show you how it is that mathematicians or people who are looking at these symbolic gestures sometimes convince each other that the rules that we use, these shortcuts we use, are in fact logical. I've been trying to do as much as I can with going back to some concepts, to some origins. Why do we call them a square root? Why do we call them a cube root? But notice that to convince yourself that one thing equals another thing, there's sometimes a way that you can prove that just by playing with both of them and seeing if you can get them to speak the same language and to look the same way. So I want to take a moment and see if we can prove to ourselves that the square root of a times the square root of b actually equals the square root of a times b. In other words, if I'm trying to do something like the square root of 12, let's do the square root of 36. Let's do the square root of 36. Is that fair for me to, in my head, try a simpler problem, which would be square root of 9 times the square root of 4? Is that okay for me to kind of look at these shortcuts? What if they were bigger numbers, smaller numbers, decimals? Well, we're looking to see if it would be square root of 9, which would be 3, times square root of 4 would be 2, and we could maybe think that the number times itself that gets us 36 is 6. So I can say 6 equals 6, and it seems like, at least for the numbers I chose in this example, the above situation is true. But how do I do it for all numbers? How do I show that there's not a magic number out there that hasn't been found yet, that if discovered would break everything that we're just talking through? How do I prove that, without having to check number by number through the infinite number of numbers that are, that this is going to be true no matter what? Well, we can just simply use our logic. If I know that I have the square root of a times the square root of b, and I want to figure out whether or not that's equal to the square root of a times b, let's just begin to play. I know that the square root of a times the square root of b, if I did know these were to be equal, then I would expect that whatever I did to one side, if I did it to the other, they would remain equal. That's a fundamental truth. So let's try something like squaring both sides. That seems to be a logical idea for what I might do to try to cancel away all this confusion. On the left-hand side, maybe I don't know that I can distribute, don't use distribute. Maybe I don't know that I can affect each individual part with the square. So let's just see what we can do by writing it out the old-fashioned way. So I have square root of a times the square root of b times the square root of a times the square root of b. So I'm saying my squaring really just means I'm repeatedly multiplying by the same thing. On the right hand side though, if I know that I have a square root, the beginnings of a square, and then I square that, I make a square from the beginnings, I should just end up at where I started, which would be the square itself. So in other words, we call these inverse operations, this idea of saying that if I have a square root and I square it, what I'm doing is I'm kind of undoing and then redoing the logic that I have in my head. I'm saying that I started with a shape, I'm undoing that to its origin, and then I'm reforming the shape. Well, that leaves me with the original shape. Okay, what else can we do over here? Square root of a times square root of b. I do know, and I feel comfortable with the idea that I can rearrange things that are being multiplied, because I know in my head that 5 times 4 is equal to 4 times 5, and that no matter how I look at any groupings of numbers, I have what's called the commutative property, this ability to kind of reorganize and rearrange my multiplication. Well, if I did that, then I have square root of a times square root of a, and I have square root of b times square root of b. Well, what that means is that I have the startings of an a square here, the origins of an a square, being multiplied by another starting of an a square, so that gets me a full a square that I'm square rooting. Well, isn't that exactly what we're talking about, where I have a times b at the very end? And if you don't believe me, I'll write it with one more step of logic. Square root of a times square root of a would be two of these instances where square root of a is being multiplied by itself. All right, so square root of a times itself times square root of b times itself. So that'd be b squared equals, well, what would that be? Square root and the squaring again would cancel out. So now I'd be left with a times b. And sure enough, no matter how I look at it, I've got the exact same idea whether I start from the right-hand side of the equation or the left-hand side of the equation. So I feel comfortable saying that no matter what, if I have a square root and I have multiplication or division, that I can affect the things individually, or I can treat them as the square root of a whole. Now, we can extrapolate and say that I did this for a square root, so I was canceling it by doing a square on both sides. But if it was a cube root, I would do the same thing with a cube on both sides. I would raise it to the third power. I'd try to look for 3 of those instances. And if it was a fourth root, I'd do that with a fourth power on both sides. So now I can even more so, I can expand my idea to say that not only do I know that this set of numbers works, and not only did it work for when I was talking about square roots, but I can work with any amount of roots. Because the logic, the process I would do would be the same, it'd just take a little bit longer. So for example, if I said the 5th root of a times the 5th root of b equals the 5th root of a times b, I could prove this in the exact same way I did above. I would just need to do 5 instances of this multiplication all the way through. Let's not do that, and let's instead just use our logic to say it would have worked the exact same way. So no matter what letter I have up here, no matter what number I have up here, we'll call it n. Any number that I have up there, if I have the nth root of a times the nth root of b, then that's going to get me the nth root of a times b. And so notice for a moment that, and appreciate all of the logic that we just put into this. We started with, I wonder if it works for a number. We then said, I wonder if it works for any numbers. And then we broke that down to say even more, I wonder if that works for any root of any numbers. By doing a small amount of work here, we've not solved one problem. We've solved an infinite number of infinite problems. We've expanded and used our logic and the symbols on our page to be able to say that no matter what you give me, and no matter the context with that root symbol, I can tell you that I'm allowed to handle these problems in a way that makes sense.